September 1943. A P-51B Mustang screams through the thin air at 28,000 feet over the English Channel. The pilot pushes the stick forward, diving toward a formation of German bombers. The airspeed indicator needle climbs past 400 miles per hour. Then 450, then 480. Suddenly, the aircraft shudders violently. The wings begin to flutter. The controls go mushy. The pilot is experiencing what aviators call compressibility. That terrifying moment when your aircraft approaches the speed of sound and the laws of aerodynamics change completely. But this pilot doesn't pull back. He can't. Because he's not hunting Germans today. He's a test pilot, and he's hunting for answers about a material that wasn't supposed to exist. 3,000 miles away, in a captured Japanese Zero fighter being examined in a Navy warehouse, American metallurgists have just discovered something impossible. The wing spars are made from an aluminum alloy stronger than anything Alcoa has ever produced. An alloy that, according to every textbook, shouldn't work. An alloy that crumbles under stress, cracks without warning, and fails catastrophically when exposed to salt air. Yet somehow, the Japanese have made it work. And now American engineers are racing against time to unlock its secrets before the next wave of bomber missions departs for Berlin. This is the story of how one Japanese metallurgist's forbidden aluminum alloy was reverse-engineered, perfected, and transformed into the material that would let American Mustangs dominate the skies over Europe. A story of espionage, scientific brilliance, and a material so revolutionary that it's still used in aircraft today, more than 80 years later. To understand why this material mattered so much, we need to go back to April 1940, when the North American P-51 Mustang didn't even exist. The British Purchasing Commission arrived at North American Aviation's factory in Inglewood, California, with an unusual request. Britain was fighting for its life against Nazi Germany. The Royal Air Force desperately needed fighters, and they wanted North American to build Curtiss P-40 Warhawks under license. But James Kindleberger, president of North American Aviation, made a counterproposal that seemed absurd. His company had never built a fighter aircraft before. Yet he promised to design and build a completely new fighter, one superior to the P-40, in just 120 days. The British, desperate and intrigued, agreed. What followed was one of the most remarkable engineering achievements in aviation history. Under the leadership of chief designer Edgar Schmood, a team of engineers worked around the clock. They incorporated every cutting-edge aerodynamic principle known at the time: a laminar flow wing, a low-drag fuselage, flush riveting throughout the airframe, and critically, they built the entire aircraft from aluminum alloy 24S, what we now call 2024 aluminum. The NA-73X prototype rolled out on September 9, 1940, exactly 102 days after the project started. On October 26, test pilot Vance Breese took it into the sky for the first time. The aircraft exceeded every expectation. It was fast, maneuverable, and had incredible range. But there was a problem. Actually, several problems. The early P-51s were powered by Allison V1710 engines that lost power dramatically above 15,000 feet. This limited them to low-altitude reconnaissance and ground attack missions. The Royal Air Force used them as Mustang Mickey-is, and while they performed well at low altitude, they couldn't escort bombers into the heart of Germany, where the real air war was being fought, at 25,000 feet and above. Then came the transformation that everyone knows about. In 1942, a Rolls-Royce test pilot named Ronald Harker flew a Mustang and immediately recognized that the airframe was brilliant. It just needed a better engine. Rolls-Royce fitted 5 Mustangs with their Merlin 61 engine, which featured a 2-stage supercharger that maintained power at high altitude. The results were spectacular. The Merlin-powered Mustang became one of the fastest fighters in the world, capable of reaching 440 miles per hour at 25,000 feet. With drop tanks, it could fly from England to Berlin and back, providing the first effective long-range escort for American bombers. By late 1943, P-51Bs and Cs were arriving in Europe in large numbers. They were winning the air war. Luftwaffe pilots who had dominated the skies now faced an opponent that could match them in speed, outturn them in combat, and most importantly, follow them all the way home to their bases in Germany. But as the Mustangs began flying higher and faster, pushing the envelope of what piston-engine fighters could achieve, a new problem emerged. One that had nothing to do with engines and everything to do with the metal holding the aircraft. Together, high-speed dives were revealing a terrifying weakness in the Mustang's design. When pilots dove aggressively from high altitude, chasing German fighters or evading attackers, strange things began happening around 480 miles per hour. The aircraft would shudder violently. The wings would vibrate, a phenomenon called flutter that could tear an aircraft apart in seconds. The elevator controls would become nearly immovable. Or worse, the nose would tuck under uncontrollably, sending the aircraft into an ever-steeper dive. This was compressibility. What happened when parts of an aircraft approached the speed of sound? At these speeds, shock waves formed over the wings and tail surfaces. The smooth flow of air broke down. Aerodynamic forces changed unpredictably, and the structural loads on the airframe increased dramatically. Test pilots reported that the Mustang exhibited severe vibration and loss of control effectiveness in high-speed dives. The aircraft's manual warned pilots about porpoising at high speeds, a dangerous longitudinal instability that could become uncontrollable. The problem wasn't unique to the Mustang. Every high-performance fighter of the era faced similar issues. But the Mustang, with its exceptionally clean design and powerful Merlin engine, could reach these problematic speeds more easily than most other aircraft. North American Aviation's engineers understood the aerodynamic aspects of the problem. They could modify wing shapes, change tail configurations, and add dive brakes. But there was another aspect to the problem that was equally critical: the material itself. At high speeds, the loads on aircraft structures increased dramatically. The wing spars, the main structural members running through the wings, had to withstand enormous bending forces. The fuselage had to resist twisting. Every rivet, every joint, every piece of aluminum had to perform flawlessly under conditions far more extreme than the original designers had anticipated. The P-51 was built primarily from 24S aluminum alloy, and E-Dreet aluminum copper magnesium alloy developed by Alcoa in 1933. It was a good material, proven and reliable, with a tensile strength of around 70,000 pounds per square inch. For the original design requirements, it was perfectly adequate. But adequate wasn't going to win the war. Not when German jets like the Me-2622 were beginning to appear. Not when engineers were dreaming of pushing piston-engine fighters even faster. What they needed was a material stronger than anything currently available. The problem was that metallurgy in 1943 had hit a wall. Aluminum-copper alloys like 24S had been optimized for decades. The basic composition was well understood. You could only dissolve so much copper in aluminum before problems arose. Add too much, and the material became brittle. Add other elements to try to boost strength, and you often created new problems: corrosion, cracking, poor formability. The aluminum-magnesium-copper system that gave you 24S was essentially maxed out. To go significantly stronger, you needed to explore an entirely different alloy system. And that's exactly what metallurgists around the world had been trying to do throughout the 1930s. The aluminum, zinc, magnesium, copper system showed incredible promise. In theory, it could deliver tensile strengths above 85,000 psi, 20% stronger than the best aluminum-copper alloys. But there was a reason nobody was using these alloys in aircraft. They had a fatal flaw: stress corrosion cracking. An aluminum-zinc alloy component could test perfectly in the laboratory, pass every strength requirement, and look absolutely flawless. Then, 6 months later, while sitting in a hangar exposed to normal humidity, cracks would suddenly appear and propagate through the structure without warning. Within hours, a perfectly good wing spar could become a liability waiting to fail. This wasn't theoretical. It was happening in wind tunnels, in test specimens, in early prototype components. The aluminum-zinc system was like a beautiful car with faulty brakes. Technically impressive, but utterly unreliable. Alcoa had explored these alloys in the 1930s, but couldn't solve the stress corrosion problem. British and German metallurgists faced the same dead end. The consensus in Western metallurgy was clear. Aluminum, zinc, magnesium, copper alloys were a promising dead end. Too dangerous to use. Too unpredictable to trust with pilots' lives. But while American and British metallurgists were giving up on the aluminum-zinc system, somebody on the other side of the Pacific had figured out how to make it work. His name was Igarashi Isamu, and in 1936, he did something that Western metallurgists considered impossible. Working at Sumitomo Metal Industries in Japan, Igarashi and his team developed an aluminum-zinc-magnesium-copper alloy with a tensile strength exceeding 60 kilograms per square millimeter, roughly 85,000 pounds per square inch. That was stronger than any aluminum alloy in production anywhere in the world. But strength alone wasn't the breakthrough. Igarashi had solved the stress corrosion problem. The solution was chromium. By adding small amounts of chromium to the alloy composition, Igarashi discovered he could dramatically improve the material's resistance to stress corrosion cracking. The exact mechanism wasn't fully understood at the time, but it worked. The alloy remained stable. Cracks didn't appear spontaneously. Components could be trusted. Igarashi called his creation Extra Super Duralumin, or ESD. The composition was approximately 8% zinc, 1.5% magnesium, 2% copper, with smaller additions of manganese and chromium. It was a carefully balanced formula that delivered both exceptional strength and acceptable resistance to environmental degradation. By 1936, Igarashi had filed patents protecting the composition. But patents could be kept relatively secret if you controlled where you filed them and didn't license the technology. Internationally, the Japanese Navy immediately recognized the value of ESD. They requested that Sumitomo develop the alloy specifically for aircraft applications. The weight savings were extraordinary. Using ESD instead of conventional aluminum alloys, engineers could reduce component weight by 10 to 20% while maintaining the same strength. Or they could keep the same weight and dramatically increase safety margins. One man who immediately understood the implications was Horikoshi Jiro, the chief engineer at Mitsubishi Aircraft Company. Horikoshi was working on what would become the most famous Japanese fighter of World War II, the Mitsubishi A6M, known to the Allies as the Zero. The Zero's design philosophy was controversial even within Japan. Horikoshi made a conscious decision to sacrifice pilot protection and self-sealing fuel tanks in favor of extreme lightness and agility. Every kilogram mattered. Every gram of weight saved translated directly into better performance. When Horikoshi learned about ESD, he calculated that using it for the main wing spars could save approximately 30 kilograms compared to conventional aluminum. 30 kilograms might not sound like much, but in an aircraft that weighed only 1,680 kilograms empty, it was nearly 2% of the total weight. That translated directly into better climb rate, better acceleration, better maneuverability, and longer range. Horikoshi requested permission from the Japanese Navy to use ESD in extruded materials for the Zero's wing structure. Permission was granted. The material performed exactly as promised. When the Zero entered combat in 1940, first over China and then across the Pacific after Pearl Harbor, American and British pilots were shocked. The Zero could outclimb, outturn, and outrange almost every Allied fighter in service. Its extreme performance came from multiple factors: excellent aerodynamics, a powerful engine, lightweight, but ESD was a critical enabling technology. For the first 2 years of the Pacific War, the Zero's capabilities seemed almost supernatural to Allied pilots. The aircraft could appear at extreme range, fight for extended periods, and return to base while Allied fighters were barely reaching the combat zone. American intelligence officers examining combat reports knew something was different about Japanese aircraft construction, but they didn't know what. Captured aircraft were rare in the early war years, and when pieces of Japanese aircraft were recovered, the material analysis was limited by both technology and understanding. Then, in June 1942, something remarkable happened that would change everything. A Japanese pilot named Tadayoshi Koga was flying his Zero during the Battle of Dutch Harbor in Alaska when his aircraft was damaged by ground fire. Koga attempted an emergency landing on Akutan Island. The landing gear sank into soft ground, and the aircraft flipped over, killing Koga instantly. But the Zero itself remained largely intact. It sat there in the Alaskan wilderness for over a month before a U.S. Navy search party discovered it. The aircraft was recovered, shipped to Naval Air Station North Island in San Diego, and meticulously examined. This was the first intact Zero that American engineers could study in detail. And what they found in the wing spars changed everything American metallurgists thought they knew about aluminum alloys. The Alcoa, metallurgists examining the Akutan Zero's wing spars, couldn't believe what they were seeing. The material was clearly an aluminum zinc magnesium copper alloy, exactly the type of alloy that American metallurgists had abandoned as too unreliable for aircraft use. Yet here it was, in a combat aircraft that had been flying operationally for years. Not only was it in use, but it showed no signs of the catastrophic stress corrosion cracking that had doomed Western attempts to develop similar alloys. Japanese had made it work. Somehow, the recovery and analysis of the Akutan Zero wasn't the only source of information. Throughout 1942 and 1943, more Japanese aircraft were being shot down and recovered. Some crashed in jungles and sank in oceans, but others could be examined. Each one provided more data points. Each sample of material could be analyzed. Alcoa's metallurgists began a systematic reverse engineering effort. They had samples of the Japanese alloy. They could determine its composition through chemical analysis, the percentages of zinc, magnesium, copper, and other elements. But composition alone wasn't enough. What mattered was the processing. Aluminum alloys are incredibly sensitive to thermal treatment. The same composition processed differently can result in materials with vastly different properties. The heating temperatures, the cooling rates, the aging time, every variable mattered. The Japanese, working under their own development program, had spent years optimizing ESD. They understood which thermal treatments produced the best combination of strength and corrosion resistance. They knew how to extrude it, how to roll it into sheet, how to form it into complex shapes without cracking. American metallurgists had to recreate all of this knowledge from scratch, working backward from samples of finished material. The breakthrough came from recognizing the role of chromium. The Japanese alloy contained small amounts of chromium, typically around 0.2%. This seemed like a minor addition, but it was the key to controlling stress corrosion cracking. Chromium affects how other elements precipitate within the aluminum matrix. During heat treatment, the alloy forms tiny particles of various compounds, zinc-magnesium phases, copper-containing phases, and others. The distribution, size, and chemistry of these precipitates determine both the strength and the corrosion resistance of the final material. Adding chromium changes this microstructure in subtle but critical ways. It helps form finer, more uniformly distributed precipitates. It reduces the tendency for certain harmful phases to form at grain boundaries, where corrosion cracks typically initiate. It's not magic. It's metallurgy at its finest, controlling material behavior at the microscopic level. By 1943, Alcoa had developed their own version of the Japanese alloy. They designated it 75S, later standardized as 7075. The composition was similar to ESD: 5.6% zinc, 2.5% magnesium, 1.6% copper, and 0.23% chromium, with smaller amounts of other elements. But developing the alloy was only the first step. Now they had to produce it at scale and get it into aircraft. This is where America's industrial might made all the difference. Alcoa wasn't a small experimental facility. They had massive production capacity, decades of experience in aluminum processing, and the resources of the entire American war economy behind them. By late 1943, Alcoa was producing 75S in quantity. The material went through extensive testing: tensile tests, fatigue tests, corrosion tests, everything the military could think of to ensure it would perform reliably in service. And critically, designers at North American Aviation and other aircraft manufacturers began incorporating 75S into new aircraft designs and modifications of existing ones. For the P-51, this meant something revolutionary. Engineers could now consider designs that had been impossible before. They could push performance boundaries that had been firmly in place. They could build aircraft that flew faster, carried more, and survived longer. The P-51H Mustang, which first flew in 1945, represented the ultimate expression of what 75S aluminum made possible. North American Aviation's engineers redesigned major portions of the aircraft to take advantage of the new material's superior strength. The wing spars, the fuselage frames, the tail structure, wherever high stresses demanded strong materials, 75S replaced conventional aluminum. The results were stunning. The P-51H weighed approximately 600 pounds less than the P-51D, despite having a more powerful engine and additional fuel capacity. With less weight and more power, the P-51H could reach 487 miles per hour at 25,000 feet, making it one of the fastest piston engine fighters ever built. More importantly, the aircraft's high-speed handling improved dramatically. The stronger wing structure could withstand higher dynamic loads without flutter or deformation. Pilots could dive more aggressively without fear of structural failure or compressibility-induced loss of control. The P-51H entered production too late to see combat in World War II, but it demonstrated what the new aluminum alloy made possible. If the war had continued, this lighter, faster, stronger Mustang would have dominated the skies even more thoroughly than its predecessors. But the impact of 75S extended far beyond just the Mustang. The Boeing B-29 Superfortress, which carried the atomic bombs that ended the war, used 75S extensively in its structure. The material's combination of high strength and acceptable corrosion resistance made it ideal for an aircraft that had to carry heavy bomb loads while operating from island bases exposed to salt air. After the war, 7075 aluminum became the standard high-strength alloy for aerospace applications. It was used in the swept-wing fighters of the Korean War era. It formed the structure of supersonic jets like the F-86 Sabre and F-100 Super Sabre. When Boeing designed the 707, the first successful American jet airliner, 7075 was there in the wing structures and fuselage frames. The material continues to be used today. Modern aircraft like the F-16 and FA-18 use 7075 and its descendants in critical structural components. Spacecraft use it where high strength and low weight are essential. It's in everything from bicycle frames to rock climbing equipment to high-end smartphones. All because one Japanese metallurgist figured out how to add chromium to an impossible alloy, and American metallurgists successfully reverse-engineered his work. The story of 7075 aluminum is a reminder that materials matter. We often focus on the dramatic visible technologies, the engines, the aerodynamics, the electronics. But underneath every high-performance system are materials that make it possible. Materials that represent decades of accumulated knowledge, countless failed experiments, and breakthrough insights that often seem obvious only in retrospect. Igarashi Isamu's innovation enabled the Zero fighter to achieve its legendary performance. Alcoa's reverse engineering enabled American aircraft to match and exceed it, and the material they created outlasted both, becoming one of the most successful and widely used aluminum alloys in history. From a captured Zero on a remote Alaskan island to Mustangs ruling the skies over Europe to modern aircraft flying today. The legacy of this forbidden alloy continues, a testament to the power of materials science to change the course of history.